Swayam Prabha. Digital India. Educated India.
Just a couple of more slides on Euler-Lagrange, and then I will say 20 minutes about Euler, because the idea is the same. There is nothing new that I'm going to say. But then when we come back, I said that this afternoon I will take one or two whatever problems of interest to you, and I will discuss. Okay. And only request so far I've gotten is for machine learning. People said that they wanted to hear. Is that
environmental flow you also said.
environmental flow? Environmental.
Sir, one is okay with machine learning. The environmental
Well, I will tell you, environmental flow is fine. No, I will do both environmental and machine learning. That's not a problem. I will do a little bit of machine learning, and I will give you some ideas. I just cannot cover all four topics. Environmental flow that I will have to tell you is multi-phase flow will be very simple. I will be using equilibrium Eulerian approach. Okay, there are no massive multi-phase flow techniques involved in the environmental flow. But the nice thing is that it is a multi-phase flow where the equations are extremely simple, but you can learn a lot from that. Okay, in that sense, it's a really exciting problem. Okay.
Possible to spend some time on data-driven CFD models?
That's what machine learning.
Machine learning models.
Yeah, data-driven. That I know that heart and people will be interested in. Now the sneezing, coughing part I have already covered at IIT. Last time I came, last year I gave, and I won't talk about that. Okay, good, very good. I know for people who are writing a code, I just wanted to say, so I told you the next 5,000 plus pickle F code. I just want you to think about, if you're writing your code, you probably already have it, so maybe I'm just preaching to the choir. So you need a time stepping, the single phase CFD kind of stuff, and this is one reason why we write our governing equations exactly the same as that single phase. So you want to use open form or fluent or something. They have their multi-phase packages, but what goes on behind the scene is almost the same. They use the same grid generator, because you see, you don't have to put, if you're using Euler-Lagrange and Euler, fluid is everywhere. Okay, so they just piggyback on everything that they already have. Okay, and then if you're doing EL, you have to have this for tracking particles. Okay. Now the pickle of the equation that the package that they said, the philosophy that we had was, hey, look, for each particle we are going to be solving ordinary differential equation. We are going to solve an ODE for position, an ODE or 3 ODEs for the velocity, 3 ordinary differential equations for angular velocity. If it's a sphere, angular orientation doesn't matter. But if you're doing an ellipsoid, you will have to track angular orientation, temperature, species. You can. So we said that user can define how many equations they want to solve. Very similar to what commercial codes would do. Okay, so you write your UDF, and here systematically you can add extra terms. So that's time stepping the particles. Then the two has to talk, so you have to decide upon your interpolation scheme. So here I want you to think about it. If you're using a first order finite volume method, you must do a linear interpolation. So you must be consistent with your underlying result. There's no point in trying to do a spectral interpolation when your flow itself is only first order inaccurate. Okay? But if you use a third order space scheme, then you really have to do a third order interpolation to get the velocity correctly. Okay? Doing more is no good, doing less will be harmful. Okay? So that's a very simple recommendation. And the projection, you have two options. You could use Gaussian, and the idea of a Gaussian is not numerical. Even the governing equation you are saying has been obtained by a Gaussian filter or whatever filter that you have. Or you could do first order projection, second order projection, third order projection, whatever you prefer. And the last point that we talked about is interparticle interactions, okay, collisions. Okay, so if you have micelles, if you have other complicated things, electrostatic forces, etc., then they will come in this well, you have to include them in time stepping the Lagrangian particle, but sometimes what happens, there are cohesive forces, okay, van der Waals forces, etc. You will have to bring them. So any additional physics you must add to this basic package. So these are the 5 steps that you will do. Now I also want to go over all the things that in the glorious equation that we wrote, all these terms appeared, okay, on the right hand side. Various modeling, okay, so you have to decide which modeling is which models are needed. Is there an evaporation? If there is none, then m dot, little m dot, you can ignore. So you may want to sort of sit down and think about what you want to model. Then the next question is, once you know that this is needed, you want to go through the literature and find the best model that is available, which is in the regime of your interest, and then you use them. Okay, so you have the code, you have the closure models. If you put them together, you have a good Euler-Lagrange simulation. Okay, so that completes Euler-Lagrange simulation. I want to go another 20 minutes max for Euler-Euler. Okay, just like I did. The basic idea is that you have the whether you explicitly state or not, you filter both phases. So once you write Euler-Euler equation, there is filtering involved, and that filter size is about 2 times, 3 times your grid size. Okay, and both phases are in Eulerian frame, and definitely you want your particles to be much smaller than your grid size. Okay, and there should be plenty of them. Euler makes no sense if you have just one particle here and a particle there and a particle there. It really doesn't make any sense, but most of us don't use it like that. We use Euler, fluidized bed, or most applications where there is a lot of particles in there, and the fact that you can't track every one of them, and that's the reason we do that. Okay. Now there is also another Euler-Lagrange method where you only track every 1 in 1,000. So in other words, if you have billion particles, you could do a million Euler-Lagrange simulation. Remember, you're tracking, but you are done averaging, because that one particle that you track is representative of 1,000. So there is averaging even in Euler-Lagrange scheme is there, but it just makes it harder. So it is little bit like it may be a sort of compromise between solving billion particles, which is very expensive, versus fully averaging and using Euler. Okay. So the advantage here are, again, the same thing. You don't need to resolve the boundary between the fluid particles, no penetration, etc. Same thing as Euler-Lagrange. And both phases, that's why sometimes they call the interpenetrating two fluid approach. You treat both of them as fluids, they are all over there, they are interpenetrating. Okay, so the other thing is that there is no interpolation, there is no projection, or none of those issues are not there anymore, right? Because both of them are in the Euler. So some of those things. The other thing is that no need to do collision detection, but you have to model the collision. That sometimes is very hard. Okay, especially we had tough time when a shock going over a bed of particles. We tried to do Euler simulation for a dense particles. It was very difficult because it wasn't able to, it would build the volume fraction to 80%, 90%, impossible volume fractions. Okay, because it didn't understand. But in Euler-Lagrange, it will never happen because the DEM will push particles literally. Okay, so there is an advantage. But when volume fraction is modest and your flow is not shock driven, you can come up with collision models that reasonably take care of everything. Okay, so that's something that you want to, and it fits very well with existing single phase code. So that's a nice thing, because if you have a code to do fluid mass, momentum and energy, you just copy and paste and you create another set of routines that take care of particulate phase mass, momentum and energy. You couple them. Only thing is that the biggest disadvantage that we are going to see is not only closure models are needed, multiple bins are needed. Lagrangian, you can take care of each particle, you can track its own size. Here, when you write a mass, momentum and energy equation, you got to tell what's the size. Now, there are techniques where they sort of look at the average size, etc., but they are not, it's not just that easy. Okay, in fact, they will make the models even more harder. So the best approach I will say is that you will have to bin them: very small particles, intermediate size particles. So like that you have to model, because you see the reason is very small particles don't get spun out of vortices. Intermediate size may spin out of vortices. Large ones may ignore. Their behavior is so small, how can you treat all of them together? If you track them Lagrangian way, that's okay. But in an Eulerian sense, you might want to use at least a few bins to, if all of them are fairly small, then you may be in you're in luck and you can, or if all of them are fairly large and they are inertial, then also you're in luck. But if you're straddling intermediate regime, that's usually the case, unfortunately. So you have to sort of think about binning them. Okay. The other thing I want to talk about is you might want to also sometimes think about mixed mode computing. That means you may want to track and you may want to use Euler-Lagrange method. I'll tell you the best application is solid rocket motor. So in solid rocket motors, there are big aluminum droplets that come out and they burn. How they burn is very important, because their propellants are aluminized. Aluminum comes out as droplets, burns. That's sort of like evaporation in a way. In fact, it evaporates, and in gas phase there is reaction and so on. You will have to treat them Lagrangian, because like I said, that they get ejected, the crossing trajectories, all sorts of stuff happen. But when they burn, they produce fine aluminum oxide smoke. That's what you see as the smoke that comes off a exhaust of a rocket. They are really small. They are like micron sized or submicron sized. So there is no reason to track them. So what one approach is to use mixed computing. Your gas phase Euler equations, your smoke is Eulerian representation, but the aluminum droplets are treated like Lagrangian way. Okay, so you can combine them to your advantage. Okay, the interface coupling must be modeled. I mean, I've said the same three things that I talked about previously, which is interface coupling, mass, momentum, energy transfer, heat transfer, etc., must be modeled, and subgrid stresses. Now there are two kinds of subgrid stresses. Fluid subgrid stresses, in other words, we take care of fluctuating fluid velocity. And now you have to have subgrid stress for particles, which is subgrid particle stresses. So, and then the last thing that I have, the modified viscosity, modified conductivity, you still have to do those things. So the reason I don't want to spend a whole lot of time is that there is nothing fundamentally different. But we did talk a lot about yesterday, I believe, or day before yesterday. The drag models are perfect for Euler-Lagrange, because you only have average relative velocity, you only have average volume fraction, and what you need is only average drag. So for an Euler-Lagrange scheme, you want to drag on a particle, what do? you go and say, what's that particle's velocity? And you subtract it from the local fluid interpolated velocity, and you say, this is my relative velocity. So you're not dealing with an average Reynolds number, you're dealing for that particle. And you're calculating what's the volume fraction at the particle around in the neighborhood. So we're not using the drag law the way it's supposed to have been developed. Then you get the drag and you apply for that particle, not for everybody. So there is a little bit of a crime being done from the way, I mean your intent is good. We say, I track particles, why don't I track them very well? What we need is better models that are good for Euler-Lagrange. Okay, they're being developed. Okay, so keep your eyes open. So they're better. So people understand that limitation. So far the models are mainly for Euler scheme. So models that are better suited for Euler-Lagrange schemes are in development. Okay, so this is sort of like the highlight I want to give. And then I want to spend another just maybe 5 minutes or so. I will show one more governing equations, what they are, and I will. So you will see that these lectures are very similar to Euler-Lagrange. So really, the gas phase equations are the same. Only thing is that you remember in the Euler-Lagrange, the feedback terms. Each particle, put a Gaussian spreading, etc. None of those things needed here. You don't have individual particles. So all the feedback, you just have to say, what's the cell average fluid velocity? What's the cell average particle velocity? That gives you cell average relative velocity. What's the cell average particle volume fraction? Put in Richardson-Zaki and you say cell average drag. Or Guitaspos relation, whatever your favorite. So in other words, lots of things become easier here. So you have a Euler-Lagrange equation, the Euler equation. That's the difference I'm trying to highlight here. You take each particle, its evaporation rate. You have to spread it with a Gaussian. Okay, here. You have to now come up with a model for cell average evaporation rate, not individual particles evaporation rate. You have to do a cell average. It's very hard because that evaporation rate depends on droplet size. In Lagrangian, you knew what the size of each droplet, so m dot L, it had a lot of information. Now this m dot, it's a lot of responsibility in modeling that term, because now you're saying I have a cell in which I have polydispersed, many different size particles are there, they are all evaporating. On average, what would be the evaporation rate? So I did say you have to model it, but the models are not straightforward. Each of them have their twist. Okay, so you want to think about, and therefore when you go pick up the model, you want to say, I want the evaporation rate not for a single size, for different sizes, and then you must have some idea about what the size distribution in your cell is, and you have to sort of calculate based on that what's the best m dot that accounts for. So in other words, you're trying to account with a model whatever this one is supposed to be here. So this way you can also see you could do a Lagrangian simulation to train your Eulerian simulation. You could do an EL simulation, more expensive. If you aren't very sure about your Euler-Euler model, one way to develop that is to do Euler-Lagrange simulation with a lot of particles. And let's say if you knew this right hand side and you say, okay, from now on, how am I going to model this? Okay, you can come up with your own model, improved model. Well, same thing with momentum equations. Okay, so now you don't have sum over droplets or particles. You have to come up with what's the average drag, average everything. Now average drag also, Richardson Zaki, I said in a monodispersed system is very easy. In a polydispersed system, it has powers, I don't know, they are based on size. So you can only see, it's a complicated job. So what people simply do is they say, well, there is a bunch of sizes, but this is the average size. But that's a really dangerous thing, because since the relations are nonlinear, calculating drag on 1 micron particles, calculating drag on 10 micron particles, calculating drag on 100 micron particles, and then averaging is not the same as saying, okay, I have 1 micron, I have 10 micron, I have 100 micron, average size is 20 microns, and you calculate the drag on it, you are completely different, because they don't swap. The right thing to do is every size drag must be first calculated, and then you must average. You must think in that term, in terms of how you model these terms in Euler-Euler simulation. This is just the energy equation, the same thing applies. Okay. The other thing that that becomes important is that when you look at the dispersed, so all the previous slides, what happened? I was comparing Euler-Lagrange mass balance, Euler-Euler mass balance equation, Euler-Lagrange momentum equation, Euler-Euler momentum equation. Okay, so I will share you all the annotated slides. You can look at the details. Okay, so you can see what the difference. And here everything again, gas phase. What would be the gas phase equation when you're tracking particles, and when you have a two fluid approach? Okay, again these are all glorious equations. Everything in it. Again, I want to emphasize that typically you want to simplify them. Okay. So now you have Euler equations, field equations for particulate field. So this is how we used to track particles. Now we have to solve this equation. So we tracked velocity. Here you have to, the important thing is that you have to add collisional effects. There you detected collision and you took care of it, so you have to add terms that will account for. So imagine that example that I talked about. There was a channel. I seed particles everywhere and let the turbulent flow go. So it's periodic, so they keep coming back. Run them, all the particles will go towards the wall. And then I said that you have to put collision to make them move. Now if you are solving this Euler-Euler, you have to do the same thing. You have to do the same thing, but now you cannot detect any more collision. You have to create a collisional pressure. Wherever there is more particle, you have to somehow calculate the pressure to be large there and pressure to be low where particles aren't there. So particle will be pushed from high density, high concentration regions to low concentration. You have to do that. So in other words, you have to come up with collisional models. I have some discussions of that in the book. So the main point is that there is a lot of modeling involved. So that's my slide. Let's see if I want to talk anything more, and if not, that will be the end of this. There's a lot of details on the the closure models of these various terms. Okay. So this is sort of like a formulation last set of lectures. So sometimes what people do, I just want to give you other things people do. They do what is called mixture model. They want, if there is two fluid, just why don't we just deal with them in a combined fashion. This is especially for very fine particles. This makes a lot of sense, because then you define the velocities are the same. It's a mixture velocity. Velocity of the particle and the fluid are the same. That's the mixture. Then you can just have a very simple set of equation: mass balance, momentum balance, energy balance of the mixture. Very simple. That's one formulation. It's also Euler-Euler in a way, because it comes out of now the good news is that you don't have to worry about size difference in sizes, etc., because all of them are moving the same. They are so small that it doesn't matter whether it's nanometer or 10 nanometers or 100 nanometers, as long as they move together. Like I said, that when you have to treat different sizes is when Stokes number is around 1. Very small ones all follow, very large ones go their own way. It's just the intermediate guys are troublemakers. Okay. So the other thing I talked about is if the particles aren't quite following the fluid, there is preferential accumulation, but there's Stokes number. Think about equilibrium Eulerian. This is something that we have used effectively. It's cheap. You can easily take care of 10 different size bins or 5 different size bins. Okay, you don't have to solve momentum equations separately for each size bin. So it's tremendous advantage. And here in this slide I've given. You see, you just solve gas phase or fluid phase equation, mass, momentum, energy, and you have to do only one equation for the tracking the mass of the particles for one size bin. If you have 3 sizes you want to calculate, you will have to write this phi d1, which is the volume fraction of the first type, phi d2 volume fraction of the second type, phi d3 volume fraction of the third type. We just have to solve 3 scalar concentration equations. And you see here, this is, by the way, this is exactly what I do if I talk about environmental flow. This is the set I solve. I mean, you may even say this doesn't look like a multi-phase flow. You're cheating. It is just a single phase equation. But this multi-phase flow problem is such that really the second phase is pretty much following the fluid, except it's just settling constantly. That's the only real multi-phase flow. And the volume fraction does change, because this is what you will do in a sediment laden river or ocean or something. That's the equation, very simple equation, but I will show you it has a lot of physics you can capture with this. So here what we are interested in is how does the sediment lift up, is at the bottom of the river, etc. How does it change? Okay. So this equation is extremely simple. So this is a simplification in the Euler domain. The mixture formulation is saying velocity is exactly the same. Here we are saying, so here you don't even have to solve this number density of the second particle, because everything is mixed. You just have to solve one set of mass, momentum and energy equation. But here we are going one step more complicated. We don't have to solve every particle sizes momentum and energy, because their velocities are freely available. You only have to solve their concentration equations. Okay. So it's a little bit more easier. The other thing that in Rand's approach, this is the kind of thing, ensemble average. I didn't talk about it. I have a section on it in the book. You can take a look at it. You again have to have particle phase ensemble average equation, gas phase or fluid phase ensemble average equation, same sort of modeling issues involved. Okay, so I want to stop there because I want to spend some time on talking about sort of little application that I have done in my group. Okay, so we'll do that this afternoon.